Good morning, afternoon, or evening. When we last left our merry world of numbers, we were talking about correlations, and let's briefly define what a correlation is. So a correlation is a relationship between pairs of variables with no consideration of causality or even time difference. And that's why the primary measure that we use is called the Pearson, named after the person, Pearson. Product, meaning you're multiplying things, and x times a y. Moment, 1 moment in time, correlation. And this is usually indicated as R. And when we look at it in the table. There's a diagonal, there's a relationship of everything with itself, A with A, B with B, C with C, D with D. This is a 1 going down, and the correlation of a D with an A, which would be right here, is the same as a correlation between an A and a D, which would be over here. Same two variables, same correlation. So what we would see generally is that this northeastern side of the diagonal is a mirror reflection of the southwestern side of the diagonal. Now, this enables us to say that there is a relationship between a particular pair of variables. And I do want to, while I have you, I do want to reiterate that if we are looking at this cell between the two variables, so let's say this is D here and this is A, this would be this cell right here. If we're asked to interpret it, there would be 3 numbers here. This top number is the actual Pearson correlation. This number here is the significance, and this number here is the N. The N is the number of observations. In your case, if you're doing a survey, the number of respondents to your survey. And so let's say, I don't know, for argument's sake, let's say that's 100. And then we have the significance. That is the first thing you would look at in the box. And you are looking for what? You're looking for a number south less equal 0.05. Less than or equal 0.05. That is the amount of error you're willing to tolerate. Now, once you conclude that something is either significant or not significant, then you're able to interpret what this means. If the relationship is not significant, you're done. There's nothing more to say. You can't talk about a relationship that's not significant as being strong or weaker. You can't, if it's not significant, you can't say it's positive or negative. It's not significant. So if this is significant, then we can look at the Pearson correlation, and the first thing we would want to look at is the sign of the variable. So in this case, there's a negative sign there. What does that mean? It means as one variable is up, the other variable is down, and vice versa. So negative, that's what negative would mean. Now, the next thing you will see is that there's an actual number here. So let's say this number is 705. So what does that mean? That means the magnitude of the relationship on this absolute scale that goes from 0 to 1 is 0.705. So what would our conclusion be if you're asked to conclude what this cell means? You would say there's a significant correlation between variables D and A. That relationship is negative, and the magnitude of the relationship is, well, you could say negative 705. That's it. Okay, that allows you to say that there's a relationship, as we all know, because we've all been told this by too many people in our past. Correlation is not causation, doesn't imply causation. It merely says there's a relationship between, in our case above, D and A. So if there's no causation, what could be the possible explanation for the relationship between D and A? Well, maybe they all came from the same parent, right? The same parent explanation. Maybe C causes D and C causes A. And that's the nature of this relationship here. So, suppose then we want to know what connection there is between one variable and another. Right, now follow my logical track here. This is pretty important. So, let's say we have this scale, and this has an X and a Y value, and this is, let's say, this is people at work who take advantage of our exercise program. We provide reimbursements for an exercise program. So this would be, and let's say there are various things that they could participate in: Zumba, dance, weightlifting, running, etc., and we reimburse all of this. So we have the dollar value of exercise that we pay for. And we also have their healthcare costs. And we want to know if providing this money for exercise is a beneficial thing economically. We want to know if the money we save, we spend for exercise somehow pays us back by reducing healthcare costs, and maybe there's some other factors that we decide we can measure. Maybe they exercise more, they're more productive, etc. All right, but we want to measure dollars spent for exercise programs and healthcare costs. So let's start with people who do not claim any exercise money. What we can do is we can look at them, that is, those people who don't spend any exercise money, and we can say that would be a 0. How much are their health care costs? So let's say their health care costs were $10,000 a year. Well, so this is $10,000 a year right here. This is 5, 6, 7, 8, 9. So if this is $10,000, what do we want to know? We want to know that the more we spend in exercise, that is, this going this way, we want to know that healthcare costs come down. And, you know, for the case of some people, they'll do a lot of exercise and healthcare costs don't come down as much. They're up here. And there'll be other people who exercise a little bit and their healthcare costs come down a lot. And let's say this looks like this. So we have 1, 2, 3, 4, 5, 6, 12 people that we measured. If we looked at this visually and we tried to determine, I wonder what kind of straight line captures the relationship here, captures the information. And it wouldn't be a line like this, would it? Because that line is pretty far from the data points. It wouldn't be this, right? Because likewise, if we had turned this line in this direction, this was actually a pretty good line, but we overshot it. We arrived here. It would be this line. Why is it this line? The simple reason for that is this line here, not these other lines, which I'm going to erase now. This line here minimizes the distance between what the line would predict, which is a straight line, and what actually happens, which is these individual instances here. So you see, the line does the worst at predicting two cases, right? This case here and this case here. All of the other occasions, observations are really very, very close to the line. So, this thing right here is called a line of best fit. Oops. And you might remember this from Algebra 2. And a line of best fit places a line where it most closely reflects, where it most closely matches what would have been predicted with what actually happened. So I just said this kind of naturally, what would have been predicted, hence the derivation of the term regression. In other words, we know what happens here, but at the beginning we regress to what would have been predicted, and we try to match these up as closely as possible. So again, hence the term regression. Now, we are not going to concentrate on how to actually do a regression, because I'm going to show you in a couple minutes that it's very easy to do with SPSS, and I can't think of anyone in their right mind who would want to calculate a regression, although it is important for you to have a logical understanding of how it is done. So please read your text carefully when it comes to regression, but read for understanding. You don't have to read for detail. You're not going to have to reproduce numbers. Now let's talk about understanding. What are some things we already know that we've demonstrated? What we've demonstrated is this. This thing we're trying to predict. Why? What we're saying about it is it begins at some point. Even when x is 0, it begins at some point. I'll show you up above. These healthcare costs, even when it begins at 0, right here, where exercise costs are 0, there is a healthcare cost. And in this case, it's $10,000. So in this case above, the y-intercept, that is, the measure of y when x equals 0 equals 10,000. Now, then we're going to have, what we're saying here is there's some kind of predictive relationship between these two variables where y depends on some function of x. Something. When something happens to x, it's going to produce a response in y. Right? That's causality. That's regression. So this thing, usually referred to as b, so in its rawest form, y equals bx plus a. A is the y-intercept. B is the coefficient of x that makes this work. So in this case, what are some things that you can notice here? One is, well, we don't have a scale here, but let's say this is $10,000 over here. So here's what we kind of can notice, that as healthcare costs, as exercise costs go up and 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 up, and finally to the point where somebody is spending $10,000 in different exercise programs, it would actually reduce healthcare costs to 0. That means there's a one-to-one relationship between healthcare costs and exercise costs. For every dollar spent on exercise costs, we save $1 in healthcare costs. This is a pretty elementary illustration. So what does that mean? What would B be here? Well, B would be, first of all, it would be a minus, right? As x goes up, it would be being subtracted by a minus. Y would be being subtracted by 1 unit. So in this case, y would equal 1x plus a. I'm sorry, minus 1x plus a. Again, this is called the y-intercept, and this is called the slope. And as you notice, a slope can be negative. A slope can be positive. A slope can be 0. What would that result in? In other words, this would be 0 times x. So no matter, again, what this means is, no matter where you go on x, it's not going to affect y. So no matter where you go on x, it's not going to affect y. Same effect out here as here. So that would be a horizontal line. So let's see, what are some things that I want to make sure I hit here logically? The line of best fit, the regression equation, the calculation of A and B, we did not do, will not do. However, this is one thing you should know. If I say that we know that this regression equation works, and here are two variables. One is, let's say this is a score on some flexibility test, and this is productivity. So the more flexible someone is in terms of their score on this flexibility test, the higher their productivity would be. And let's say I ask you, if we know that this regression works, what's the difference in productivity between two people? One with a flexibility score of 30 and one person with a flexibility score of 50. So what's the actual productivity difference? So you would throw 30 into this equation. 7 plus 40. This is 21 plus 40. So they would have a productivity score of 61. Now instead, you take this other person who is 0.7 times 50 plus 40. So that would be 35 plus 40, or 75. You are asked what would be the difference in productivity, and you would say the difference between these two people is that if this is person A and this is person B, A and B, person B should be 14 additional points, 14 points above person A in productivity. And you are kidding yourself if you do not think that Rutgers has some kind of idea when a student is admitted, what their success score is going to be, however Rutgers measures it. So you use things that you know that establish some kind of pattern for expectations, and you use it to make predictions, and you keep on tweaking it. That is absolutely right. But you use that formula to make ongoing predictions and confirmations. Okay, so let's complicate this a little bit and also give you a realistic example of how regressions are used. And here's a complication. You want to measure the potential for success, or not potential for, but success at Rutgers. And you would expect that everybody has some level of possibility of being successful at Rutgers. And then you would say, you know what? We believe that the higher your X, the higher your Y of success at Rutgers equals. And your X is your SAT scores. Plus, we believe that C times Z also factors into success. And this might be your high school GPA. Plus A. Now, obviously, we can go on and on here for various, include various factors. If we have a formula that works, then we're assuming the formula works. And SPSS, as well as other statistical software, will help us figure that out. I'll show you that in a second. Now, suppose then we had this number, and then I gave you SAT score for a student and I gave you high school GPA for a student, and I told you we have a formula that works, and the formula is, I don't know, 0.2 times SATs plus 0.4 times high school GPA plus we'll say plus alpha. Everybody has at least a 20% chance of success. So then suppose I gave you someone's SAT scores, gave you the high school GPA, then you should be able to figure out what this predicted Y is. That's it. That, by the way, is called multiple regression. Why multiple? Because you have multiple variables. Good. Okay, let's go and take a look at a regression question using SPSS. So while SPSS is loading, let me highlight some questions that you should be able to handle tomorrow. In terms of regression in the SPSS section, you should be able to open up SPSS. You should be able to open it to data view, which you see has been opened here, and you should be able to click this stuff aside. Okay, you should be able to click that stuff aside. What I'm likely to do is give you some raw data and ask you to input the data. So what you would do here is, let's say this is a certain variable and you're rating it 5, 4, 6, 7, 8, like that. And then you would go to the next variable and you'd put 7, 4, 25, 14, oops. Four, 35, 14, 25. So you should be able to load it. You should be able to go to variable view, and you should be able to give these names, whatever the name is. Test name 1, test name 2, like that. You should be able to put it down as whatever kind of variable it is, whether it's nominal, ordinal, or scale. We pretend it's scale in both cases here. And get back to data view, and then you should be able to do a regression equation. Okay, you know what? So let's get some data here. Let's say we have 20, 35, 40, 30, 35, 55, 15, 40. And then we have 5, 1, 2, 7, 8, 9, 3, 2, 5, 8. And we want to see if these have anything to do with each other in some kind of causal fashion. We want to know, we're going to call, let's see, variable A we're going to call this you might recall this. We're going to call this assessment, and we're going to call the second one productivity, or job success, or whatever you're measuring here. So now we have two measures, and we want to know if this test that we give job candidates does a good job at measuring productivity. Got it? So go to Analyze here, and we want to do a regression. We want to do a linear regression. And let's see, what are we trying to predict? That would be the dependent variable, right? That is productivity. We want to predict productivity. That is also called often the criterion. It's the criterion, the thing you're trying to predict. This assessment that you're giving people would be an independent variable. You want to see to what degree does it predict productivity. Also, you call it a predictor when people use regression speak. And there's nothing in particular that we need to click here. We'll just go for the regular stuff. Click OK. And here is what we have. So here's the regression. Now you see this R of, you know what, let me pause for you while I click and paste this into a Word document. Okay, so here I've opened up the Word document, and I'm just going to keep the source formatting for everything I copied. And now let's take a look at what we have here. So, as you can see, what SPS did was entered the variables, entered the assessment variables to predict dependent variable. If I asked you for a model, you would say assessment predicts productivity. And what would your hypothesis be? That assessment on this test predicts productivity. What would the null be? It is not true that assessment on this test predicts productivity. And if we look down this model summary, you'll notice that the R here is 937. What is the R? Well, you know what the R is. Correlation. R. Correlation. And then we have an ANOVA. What is this ANOVA for? Well, the purpose is it took the predictions and the estimations and the actuality, and it says this formula is significant. Good. That's good, right? So, now what's next? Are the coefficients. Now, in your mind, you need to cross this out. There is a reason to have this. We're not there at that place now where you can understand that. We are not there at this point. So I want you to concentrate instead on what we have here. So do you remember this formula? Y equals B times X plus A. A is a constant. That's the y-intercept. and this is times the assessment. So this looks like this number here is a 1.39, which is added, it's plus, right? And this is 0.18 times assessment, which is our x. That equals our y, which is productivity. We have the formula. So there's nothing else to make of this. We have the whole thing here. Okay, so you know how to use SPSS to do a regression. You know how to interpret it. So what this means is that everything begins at, this is 1, this is 2, this is 4, this is 6. Everything begins at 1.39 here, should be, let's say, right here. It's the y-intercept. And does it have a positive slope or a negative slope? It has a positive slope, which means it does not go down, it goes up. Now, a positive slope of 1 would mean for every 1 you go over on this, you go up by 1. So a positive slope of 1 would be approximately a 45-degree angle here. This is less than 1. This is about a fifth of 1. So this slope would be approximately like that, right? So this represents that. Not this. So you should be able to look at formulas and you should estimate what a formula looks like. So there are plenty of potential questions that I just created, gave you an idea about, and those are questions like this. So if I gave you this, and I could actually put some lines here. And if I gave it a line here, you know that y equals bx plus a. What is a? A is a minus y. A is a minus number here, so this might be minus 10. What is b? B is a plus number here, times x. It looks to be like right around 1, say 0.9 x. So, just looking at a line, you should have a good idea of what it looks like. All you need to know is this is the y-intercept, and this represents the slope of the line. This is positive, this is negative, this is 0. No slope. It's the same everywhere. Those are questions you should be able to do. Good luck in your studying. I will see you very, very soon. Bye-bye for now.